Here we have a couple more dynamics problems. The first problem says you have two hanging masses connected by a rope, and the whole system is accelerated upward. And we're looking for the tension and the rope connecting the two masses. So we'll start by drawing a picture. And call this mass A connected to mass B. And each of these ropes has tension in it. We call this tension 1 right here, and tension 2 connecting the two masses. Now we're asked to find tension 2. This is what we're solving for. So the next step here is maybe to draw a free body diagram. Maybe we'll draw a free body diagram for each mass. So let's start with mass A. And the x direction has nothing interesting going on, so we'll just draw it in the y direction. And here's our object. And for the first mass, we simply have weight acting downward. So that's weight A. We also have tension 2 acting downward. So we'll put that over here. This is T2. And we have tension 1 acting upward. T1. Okay, and we can draw a free body diagram for mass B. Mass B is a little simpler because all we have is weight B acting downward and tension 2 acting upward. So it seems like Newton's second law applied to mass 2 might give us something useful, but let's go ahead and apply it to both masses just to see what we get out of it. Okay, so step 3 here is to fill out Newton's second law using these free body diagrams. Right, so for mass A, we say the sum of the y direction forces is mass A times acceleration. And again, that acceleration is a number that's given to us. In fact, we could draw that on this diagram. We could say this whole system is accelerated upward. Okay, so the sum of the y direction forces looks like we have T1 upward minus a T2 downward minus a weight A also downward. So that's MA times G equals MA times A. Okay, so here's one equation and two things that we don't know. Right. We don't know T1, we don't know T2, and we're solving for T2. So let's turn our attention to mass B. We have the sum of the y direction forces is mass B times the acceleration. Right, it's the same acceleration for both blocks. And for mass B, we have T2 minus the weight of B. The weight of B is MB times G equals MB times A. And this is one equation and one unknown. In fact, it's the unknown we care about, right? T2 right here is what we're looking for. So it looks like I actually don't have to use the equation that I got from mass A, but that's okay. It's still worthwhile to have filled it out. So looks like I can simply say T2 is mb times A plus mb times G. I can fill in numbers for that. That's 225 kilograms times 0.67 meters per second squared plus 225 kilograms times 9.8. And the number I get out of that looks like 2,360 newtons when you round this to 3 significant figures. Okay, so let's look at the second problem. Second problem says I have a 50 kilogram trunk pulled by a rope along a level surface at a constant speed. All right, the rope makes an angle with the ground of 15 degrees. That's above the horizontal, and we're given the coefficient of kinetic friction, and we're asked to find the tension in the rope. So let's draw a picture again. So we have some trunk, and it's being pulled at an angle of 15 degrees. It has a mass of 50 kilograms, and the coefficient of kinetic friction, mu sub k, is 0.40. So I draw this little curly arrow pointing at the interface, just to remind myself that there's friction there. Alright, so I'm not trying to label mu k as a vector. Mu k is a scalar, right? It's a unitless number that relates the size of the normal force to the size of the friction. We'll see that in a second. So the next thing I can do is draw a free body diagram. Alright, so set up some axes here. And put my object at the origin. So weight is the easy one. Weight's the one that points straight down. Tension points off at some angle. Right, there's 15 degrees. And maybe I'll break that into x and y components because it's convenient to do it right now. We have a normal force, and the normal force points upward, and because this is not accelerating up or down, I need the net y direction force to be 0. That means that the normal force plus this tension in the y direction plus the weight need to add up to 0. Right? So you can see what's left over when I add the weight and the tension. Should be some small arrow pointing upward. That's this one right here, F sub n. And then I need to put the frictional force in. So we're told that this block is traveling to the right at a constant speed. Constant speed means 0 acceleration, and 0 acceleration means no net force. So this is a case of dynamic equilibrium. Okay, so again, no net force in either direction, so the frictional force needs to counteract the x component of tension, which means it just needs to point to the left and be about this long, right, about the length of tx pointing to the left. So that's f sub k. That's our free body diagram. So now that we have a free body diagram, we can fill out Newton's second law. So in the x direction, the sum of the forces equals mass times a sub x, which again is 0 for this case because this is an equilibrium case, right? Dynamic equilibrium. So that gives us that T sub x minus the frictional force equals 0, or that T sub x equals F sub k. Alright, now I'm going to substitute some expressions for these two values to get this closer to things that we have already, things that we're given or things that we're solving for. So T sub x can be found in terms of this total tension, and that's what we're solving for, is the total tension. Right? So T sub x is adjacent, so that's a cosine. So it's T cosine 15 degrees. And if you remember, the frictional force, the kinetic frictional force is a constant value, and it's mu sub k times a normal force. So that is one equation and two unknowns. Okay, we don't know tension, and we're solving for tension. And we don't know the normal force, so we need another equation. So we can do Newton's second law in the y direction. So that's the sum of the forces in the y direction equals mass times the y direction acceleration, which again is 0 for this case. So I can add up all of these forces. We have a normal force, F sub normal. We have T in the y direction, and we have weight pointing downward. And all of that adds up to 0. Alright, so we can do one more line here. That the normal force plus T sine 15 minus mg equals 0. And that's a second equation with the same two unknowns, right? The normal force that we don't know and the tension that we don't know and we're solving for. So I'm going to label these two equations as maybe A and B, just for convenience in the next step. Right? So at this point, it's just a math problem. Right? At this point, it's two equations and two unknowns, so I can do whatever method of solving this system of equations that I feel comfortable with. What I'm going to do is solve A, so I'm going to rearrange A to solve for F sub n, the normal force, and when I do that, I get T cosine 15 divided by mu sub k. Right, now I'm going to plug that into B, and when I do that, I get T cosine 15 over mu sub k plus T sine of 15 equals mg. And it looks like I can factor out this t here. So I have t times cosine 15 over mu sub k plus sine 15 equals mg. Now it looks like it's pretty obvious. I can plug the numbers in here and solve for t. So plugging numbers in, it's cosine 15 divided by 0.4 plus sine of 15 equals 50 kilograms times 9.8. And if you solve this for t, you get 183.3 newtons, or rounded to two significant figures, that's 180 newtons.